for types of filters, different applications, characteristics, heat matching, and some digital signal processing filters. This is a start showing your typical high power filters. T, it's called a pi, because the pi looks like a symbol pi, and the T looks like a D. In both cases, they're high pass filters, so they block low frequency and the cutoff frequency. And the cutoff frequency for these is this formula. Instead of 1 over 2 pi times the square root LP, it's 1 over 4 pi. Partly because of the way that the capacitors or the inductors are split equal within half. That is what gives you the 4 in the formula instead of 2. So, like I said, the T that we're going to see, it's a high pass because if you think about it, at low frequency, distance. Basically, cutoff for red, then it's going to be 3 down. So the thing to remember is that as the frequency goes up, the capacity reactance decreases, becomes more, less reactive, and the inductive reactance increases. So it's going to pass less. So what's the frequency response of a heavy? The series capacitors. Configuration of the complex by having active step. Theory. It's like the heat. Power to pass the low pass high some of these would have also you can find that work at the back. That's called conjugate matching. The impedance is a complex. If you do a conjugate match, you're going to take the reciprocal of imaginary. So if I had, say it was 50 ohms real and 50 ohms, a plus 50 ohm reactive, meaning it's inductive, the conjugate match for that is going to be 50 ohms and minus 50 ohm capacitive, which should cancel out. All you see is the resistance. It gets a little more complicated when you're trying to change the actual R value in addition to getting rid of the reactance. That's the only part you need to remember. One of the advantages of the pi network as opposed to a simple L, which is like half of the T, they have a little better thing than mine. Right. And you can, because of the configuration, you can manipulate the components and affect the Q of the circuit or its bandwidth. So if you want to have a match over a wider bandwidth, you can do it with a pi type filter or network and get a match, maybe with a little loss, but over a wider frequency range. How does an impedance matching circuit transform a complex impedance to a resistive impedance? Negative resistance, transconductance, dissipation. Magic. What you do with a Smith chart. Pi L is a pi network with an L network attached to it. It's a semiconductor attached to it, which looks like an L part. Normally, they would use those on a vacuum tube amplifier to help match the 50 ohm output, and it has a lot better harmonic suppression than just the pi network itself because of the additional inductance of that component, which describes a pi L network. Pi network is an L. What's the purpose of adding an inductor to a pi network to create a pi L network? Okay, we can use those piezoelectric crystals we talked about to make a filter. And that was very common in older radios to have in a better radio, you had a crystal lattice IF filter, which would give you very steep skirts on the filter and passband. And ideally, what you would want was a passband that looks like a square, almost vertical, flat, and vertical. You can't quite get there, but the crystal lattice filters with enough stages got pretty good. And one of the things that you, for the filter is the tape factor, okay, which is how fast the slope of the leading edge and trailing edge increase and decrease. So the sharper the rubber, the better it can reject adjacent signal. That's the whole point. You want to try to only pass the IF frequency that normally you're using and reject any frequencies that are higher or lower than that IF passband. And if you get signals that are coming in slightly at different frequencies, they're going to be very close to your IF frequency. That's part of the selectivity of the receiver based on your IF passband filter. This is kind of what one looks like. I've seen them with maybe 10 or 12 crystals. It's very complicated and much squarer response to this one. This would be a very simple. And each of these filters is a slightly different frequency in order to give you this passband. And don't ask me how to calculate them. What is a crystal lattice filter? Which of the following describes a receiving filter's ability to reject signals occupying an adjacent channel? How steep the we have different types of filters. There is vessel, Butterworth, Chebyshev, and elliptic. You have to remember all of them. The Chebyshev, and there's some reference, is used quite often. It's got a very, if you notice, fairly sharp curves. The only thing better is the elliptic. It does have what we call passband ripple. See that in the passband, the amplitude or the insertion loss is going to vary. Ideally, you'd want it to be flat, which you get with a Butterworth or vessel, but you don't get the steepness of the skirt, so everything's a trade-off. And then the elliptic has steeper skirt and less passband ripple. So those are really the two, the Chebyshev and the elliptic, that you have to remember for the exam.
Robert?
Yes.
Is there something in the shape of the elliptic that actually equates or approximates an ellipse?
elliptical.
I'm sorry?
That I don't know why it's elliptical, so I can't answer that question.
Okay, thank you.
One thing it does, if you notice the out of band down here, you get some ripple there, which may be more than some of the others. So sometimes that has an effect. What I was just showing down here. Instead of going smoothly down like to infinity, you'll have some peaks.
Actually, it's possible if you look at the ripples on the top of the trace for the elliptic trace on the graph, the curves for that are much flatter. And so maybe if you put a couple of them together, it's more like an ellipse.
I don't know. Could be.
Yeah.
So which type of filter has ripple in the pass band and a sharp cutoff? Debbie show. It could have been elliptic, but it wasn't one of the answers. What are the characteristics of an elliptical filter? Okay. Some applications where you have to use a filter, you pick the type. You pick the type depending on that application. So the example here, if you had a repeater, let's say 2 meters, to implement the duplexer, they normally use what's called a cavity filter. Yeah, I think I got a picture of one coming up. I have no idea what it is. They're very low insertion loss, which is one of the things you care about in the filter, is how much signal loss you have going through the filter, even in the pass band. Very high selectivity, upwards to 100 dB. And just because of the way they're constructed, they can handle very high power levels. Although most repeaters are only less than 100 watts, especially at 2 meters. This is kind of what cross-section one looks like. And it's a cylinder cavity that's designed to be resonant. You have this little input loop and output loop that are connected to the coax connector. So that's how you feed it, and the output back out. And you have a slot inside of this rod in the middle that allows you to vary the inductance of that, and that's how you tune it. So you tune it to the resonance point or cutoff frequency. So it's a manual tuning, mechanical type of filter. Oh yeah, somebody get really good. Here's another type called the helium, which you see on some transceivers, where the input-output loops are these helical coils in there, and it's another kind of resonant cavity sort of thing. And You know, you're almost getting up into the microwave where you don't have conductors and tubes. Very the size of the tubing. But in both cases, they have very high Q, very low insertion. So which of the following filters is used in a 2-meter band repeater duplexer? You were paying attention. Which of the following is most frequently used as a bandpass or notch filter in VHF and UHF transceivers? Yes, why is that? I think I remember going through this. I thought I went back and added something to the chart. Was it there and I didn't mention it? It could have been a silent key, but